a battery tester. Nice little gizmo, easy to handle because all you have to do is to open it up, put the cell in this case, and it goes across and says it's on the green, so that should be okay. It can handle lots of different sizes of cells from, it says it can use down here, it calls it a mini cell, but says a button battery on the actual display, which is a bit worrying to me. I wouldn't want to test them on because of the current that it draws, and it can go right up to a D-size cell. So that excuse me, that seems good. On the end then we've got a couple of contacts, one which has a couple of lines across it here, so you can't get the battery the wrong way round. So let's try with the battery to start with. We've got to have the narrow bit up at the top so it goes in between, and that one isn't very good. It's rechargeable and it needs recharging. Can we get it again? Where are we? There we are. Needs recharging, but if we use a cell which is a battery which doesn't need recharging, then that goes across and shows us that it's full. How's this different than a voltmeter then? Well, if we look on the back, it says, if we can see it here, yeah, when the battery, for a 1.5 volt battery, it has a load of 4 ohms. And for a 9 volt battery, it has a load of 215 ohms. It also says that the replace is about 0.9 volts for the 1.5 and down at 5.3 for the 9 volt, which I would have thought was quite low. Anyway, so there it is, that's what we've got. Very different cells. I've taken the screws out so I can get it apart easy, so I've just put some bits of sticky gunge on the end so I can pull it apart, and then I can just very carefully take the back off, very carefully. Probably won't gum now. And there it is, there's the back off. Comes away, and what we find is that the slidey bit has a wire to it which has to go to the meter. I've replaced this wire because it broke on the original one, just soldered it on. It has a sort of cable clamp there. I've tried to use more flexible wire than the original so that it can go up and down more times. Up at the top here then we have a negative connector which acts both for the cell, the 1.5 cell, and for the 9 volt battery. The wire from this comes through onto the meter, and the one from the 12 volt or 9 volt over here comes onto the meter. If we look at the meter then, what we can see on the top is a circuit board. Now on this circuit board you may notice that this resistor here is physically bigger than the other three. That's because I managed to blow it out. I managed to put 9 volts onto the 1.5 volt side, that's this side here, and that then blew this resistor out. Probably took a couple of amps. So I could tell it had gone because it had the little black dot of death in the middle of it where it had actually exploded. So this in fact is, if I can see it somewhere, come on, where are we? If we go down to there, this is in fact a 4.7 ohm resistor instead of the 3.9, because of course I didn't have a 3.9, but this should do the job. It won't take quite as much current as a 3.9 ohm resistor, but it'll do the job for what we want. The meter then is soldered straight onto the circuit board, making it a nice easy construction, but the resistance layout is, I found, a little bit complicated. What we have is here, this is the layout. What we have are 2200 resistor, and what this actually is a 220 ohm resistor. The naught on the end means that we don't add anything onto the end, as opposed to this here, which has a 1 on the end. So this is 3600, because we put 10 on because of this. So this is 3K6 ohm resistor. Here, once again, we've got a 5600. Well, it's O on the end, so we forget about that, and it's a 560 ohm resistor. And here we have a 3R9, so that is a 3.9 ohm resistor. Found it difficult to understand, so I redrew it like this. So what we can see here's the 220 ohm resistor, which is the current flows through that, so that it's better than the multimeter because it's actually drawing a current. Over here we have the 1.5 volts in, and that actually goes through the 3.9 ohm resistor. This said 4 on the back, but I suppose 3.94 is near enough. And then we have the meter itself, but to make it so it does a different full scale deflection from the 9 volt and the 1.5 volts, then we have these resistors here, which are going to drop some voltage across them or reduce the current down so that the meter has a full scale deflection. Yeah, interesting thing. So can we have a look and see what happens? Well, if we do a few measurements, let's try, what can we measure? Let's try the 1.5. So first of all, we'll connect this to our meter, and we'll connect it to the 1.5 connection. So that means connecting it onto there and onto the 0 volts. So is there a 0 volts somewhere? Hopefully I can pick up a 0 volts there. Have I managed that? Oh no, I've got to connect the battery in first of all. So I connect the battery in, hopefully, and I see that my battery is at 1.52 volts, and it's taking something like 280 milliamps on the 5 volt range. So that's taking quite a bit of current. Doesn't want leaving on too long, else the battery will eventually run down. We can do the same thing on the 12 volts, but what I'll do for this, instead of using a battery, I'll use a power supply, so that hopefully we can see we've got 1 volt on there. If we look at our meter, it's come across to not quite charged. So what I need to do is to change my input from the 1.5 volt input, which is how I blew it up before, to the 12 volt input, which hopefully we can catch on to there. So now we've got 1.6 volts coming in, but we're on the other range, so the meter doesn't go very far across. If I increase the voltage, hopefully we can see that as it goes across, the meter goes across until it reaches about 9 volts, and at 9 volts then we've got about 40 milliamps going through it. So that seems all okay, seems to be what we'd expect to find. If we have a look at some of the maths then, this is maybe the boring bit or the interesting bit, whichever way around you look at it. If we look at the current from the 9 volts, then V equals I times R. So we can swap that round to give us I equals V divided by R, which is 9 volts divided by 220 ohms. And that actually gives us the 40 milliamps that we measured. Quite impressed with that. However, with this on the 1.5 volts coming in, we got I equals V divided by R again, 1.5 divided by 4.7, because of course I blew out this resistor, and that should give us around 319 milliamps. So a reasonable amount of current to be taken to measure it. Can we go any further with this? Well, one stage further that I'd like to know is how much current is actually flowing through this meter. To do that then, what I can do is to look at, rearrange my diagram so that I've got my meter here, and I can measure the resistance across it as 174 ohms, but that isn't just the meter, that's these other resistors as well. Since this and this are in series, we can add them together to give us this, and this are in series, so it gives us this. So now what we've got is the meter with these two resistors in parallel across it. So we need to know what one resistor would replace those two. And if we go through the old formula, 1 over RT equals 1 over R1 plus 1 over R2, we work out and we find that the combined resistance of those four resistors is going to be about 480 ohms. So that then enables us to start looking at what the resistance of the meter actually is, because here we've got the meter in parallel with 480 ohms, and we know the total resistance is 174, so we can come back to our old formula again. 1 over RT equals 1 over the resistance of the meter plus 1 over 180. If we go through that, then we find that the resistance of the meter we calculate to be 273. However, what I did was I disconnected the meter and measured the resistance with it disconnected and found that to be 269, very close to my 273. Once we got the resistance of the meter, then we can start calculating the current through it. So if I want to know the actual current that's going through the meter, I know the resistance of the meter, and I know the resistance of its protection resistor from up here. So here we had the meter coming through the protection resistor to the meter, and therefore we know both resistances now. We know the meter is something like 270 something, and the protection resistor is 3600. We can add those together because they're in series to give us this particular resistance here. We can come back to our V equals I times R, or I equals V over R, and that gives us 9 divided by this massive number to give us something like 2.3 milliamps. So what we're getting is about 2.3 milliamps through our meter. We could of course then calculate the voltage across the meter, which seems to work out at about 0.06 volts actually across the meter. We could measure that, so if we want to measure it, we have our trusty meter, turn it on to the volts and connect it across the meter, this meter here. And what we have one connection there and one connection there, and if we now reconnect this, it shows us, can't see it, but if we can't turn the light on, shows us that we have about 0.4 of a volt across, as opposed to the 0.6 which I'd calculated. So that hasn't worked out too well. That goes off very quickly. Hasn't worked out too well for the voltage across the meter, but it's of the same sort of order of magnitude, about 0.4 of a volt. So yeah, quite an interesting look at this sort of battery tester. Lots more I could go into, but I think that's enough for now. So it's bye now. Bye.